Hello students, myself Dr. Smita Agrawal. In today's video session, we will discuss relations in discrete mathematics. Before this, we have already covered the topic set theory and functions in discrete mathematics. So let us start today's video session. In today's video session, we will cover the topic relations and its introduction along with the representation of relations using matrices and directed graphs. So let us see the first thing, that what is a relation. Now when we think of a relation, so let us give you some example of real life. For example, if we say that X is studying in city Y, so X is a set of people or student you can say, and Y is the set of cities. So that means here two sets are related to each other. Similarly, if we say that person A is born in city B, then A belongs to the set of persons and B belongs to the set of cities. So in this way again these two sets are related with the relation born. So that was the example from the real life. Now, so we can relate these examples to our topic relation in discrete mathematics. So in discrete mathematics, when we talk about relation is a way of representing relationship between any two sets. Let us see some more examples of it. So we can say that relationship between program and its variables, it is a type of relationship. Similarly, relationship between pair of cities are linked by the railway network or air traffic or air network. So these are all the example of relation in discrete mathematics, or you can say in real life. Now the next thing that comes to our mind is, why are we studying relation here? Why do we study relation? What is the need of it? So let us see the need of relation. Actually, there is a topic relational database management system, and in that whole concept is based on the topic relation. In that relational database management system, all the records are arranged in a form of table, that is called a relation. So that you will study in the subject database management system. So now let us move to the real topic, that is relation. Now moving further on the definition of the relation, I would like to recall some topics from the set theory that are the base for this topic relation. So let us first discuss the term Cartesian product. So when we are having two sets A and B, then their Cartesian product is defined as A cross B, where A cross B can be defined as ordered pair A comma B, where element A belongs to set A and element B belongs to set B. Here this A comma B is called ordered pair because here the first element A is belonging to the first set A and the second element B is belonging to the second set B. So the next thing that you have to keep in mind, that is most important here, that these are called ordered pairs because here order matters. So now what do we mean by order matters? So let us see one example for it, that we are having an ordered pair of like 4, 7 and we are having a less than relationship here in this ordered pair. So that means this relation is true here because obviously 4 is less than 7. So the relationship less than is true here. Now if I change the order in this pair, that means if I write this pair 4, 7 now as 7, 4, and now if we see this relationship again, that is less than relationship, now we can see that 7 is obviously not less than 4. So that means this relationship less than is false here. So So that's why we say that order matters. One more thing that you have to keep in mind for the Cartesian product, that if we are having Cartesian product of two sets A and B defined as A cross B and Cartesian product B cross A, then these two are not equal. Why I am saying this? So let us see one more example for this. So let us say that we are having set A comma B and second set B with elements 1 comma 2. So if we are defining a Cartesian product A cross B here, so what it will be? It will be A comma 1, A comma 2, B comma 1 and B comma 2. Similarly, when we write B cross A here, what we will get? We will get 1 comma A, 1 comma B, 2 comma A and 2 comma B. Now, if we take first ordered pair of this A cross B and first ordered pair of this B cross A, so are these two same? That means are A comma B and 1 comma A, these two ordered pairs are same? No. Why? Because here you can see that this A, first element of this ordered pair, belongs to set A and second element of this ordered pair belongs to set B. But here the first element of this ordered pair 1 belongs to set B and this element, second element of this ordered pair, belongs to set A. So that means these are not equal, these ordered pairs are not equal, and that's why similarly we can say that A cross B is not equal to B cross A. So this was all about the Cartesian product and ordered pair. Let's see some special case of it. Special case means if the Cartesian product is defined on the set A itself, then we can write it as A square and it is denoted as A cross A. Similarly, if this concept is extended to the n sets, then it can be defined as A raised to the power n, or we can write it as A cross A up to n times. So this was all about the basic concepts on which the relation is based. So now let us see the definition of relation in vast term. So actually relation is the subset of the Cartesian products of the given sets. So first we have a look on certain type of relations. So we will start with n array relation. So let us suppose that we are having n sets A1, A2 up to An. Then a relation R on these sets A1, A2 up to An is the subset of A1 cross A2 cross up to An. Right? Now, if we say that all these sets are same, that means if Ai equal to A for all I, then R is called n array relation on set A itself. So there are empty relation and universal relation. Now, if this subset for which relation is defined, this is empty set, or we can say that if R, that is a relation, is phi, then this relation R is called empty or void relation. Secondly, if this subset is the whole set, or we can say that if we are defining n array relation and R equal to A1 cross A2 cross up to An, then this relation R is called universal relation. Right? Now let us move to the term binary relation. So if you see that if R is an n array relation, then it is the subset of A1 cross A2 up to An. Now if this n equal to 2, then this relation is called binary relation, and when we will talk about the term relation in the rest of the topic, we will generally talk about the term binary relation. So let us move to the definition of binary relation. So how can we define the term binary relation? So let us suppose that we are having two subsets A and B. Then the binary relation can be defined on these two sets A and B as a subset of A cross B, where we can say that if R is a relation that is defined on A cross B, so that means what it will be? R will be the subset of A cross B, and there is some ordered pair A comma B belongs to R, obviously, where the element A belongs to set A and element B belongs to set B. So in this way, what we can say? We can say that element A is related to element B. It can also be written as A related to B. So now let us see some example of it. So let us say that we are having two sets A and B. A is the set having elements A comma B and B is the set having elements 2, 3 and 4. And let us define a relation R on it as A comma 3, B comma 2, B comma 4. So R is obviously a subset of A cross B. A cross B is the Cartesian product here, and R is a subset defined on A cross B. So R can be defined as a relation from A to B. Now, if we define a binary relation on a set itself, so how it is defined? If we define a binary relation on a set A, then that relation R is a subset of A cross A. So let us see some examples of it. For example, taller than. So taller than is a relationship on triple. So if we say that there is an ordered pair A comma B that belongs to relationship taller than, it can be true only if a person A is taller than the person B. So this is one example of relation on a same set. Similarly, we can define a greater than equal to relation on a real set R. So how can we write it? We can write it as x comma y belongs to relation R such that x and y belongs to R and x is greater than equal to y. So as you can see that we are writing it in the form of a predicate. So that means we can also define the relation in a form of a predicate. Let us see some more examples on it. So let us say that we are having a set A containing elements 1, 2, 3, 4, 5 and 6. And if we are defining a relation R such that A divides B, so obviously it can be said as a relation from A to A, then ordered pair in the relation R are, see that we are defining this relationship R on this set A itself. So if we say that A divides B, that means in the ordered pairs the first element should divide the second element. So that means the ordered pair in this relation R would be 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, 2 comma 4, 2 comma 6 and 3 comma 6. Be A to A here. Let us move to the next example. Let us suppose that we are having again a set A containing element 1, 2 and 3. So these are all the ordered pairs that will be there in the Cartesian product of A cross A. Now, if we see this A cross A, this is an universal relation of A, and if we see it as phi, so phi is also a subset of A cross A. So phi will be defined as an empty relation on A. So there can be more relationships defined on this A cross A, and what are those and what will be the ordered pairs in those relationships? Let us see that. So the first relationship that can be defined in that set is equal to. This is also denoted as sometimes delta, and we will be using this notation later in this topic. So, if we say that we are having this set A and we are defining an equal to relationship. So, what will be the ordered pair in that? 1, 1, 2, 2, 3, 3. Similarly, less than relationship, the ordered pair will be 1, 2, 1, 3, 2, 3. In greater than relationship, ordered pairs will be 2, 1, 3, 1, 3, 2. Now, in less than equal to relationship, the ordered pair of type 1, 1, 2, 2 and 3, 3 will also be there in addition to the ordered pairs that are defined in less than relationship. Similarly, we can define greater than equal to relationship. Another type of relationship that can be defined here is divide. So, these are the elements which are defined as A divides B. So, the ordered pairs here are containing the elements where A divides B. Similarly, we can define another type of relationship, that is multiple of. Now, we will see that how we can represent the relation in two different ways. So, there are two different ways in which we can represent the relation. Those ways are using matrices and using graph. So, let us first see the way of matrix. So, if we are having a relation R on a set A and the number of elements in set A are n, then a relation R can be represented as an n cross n Boolean matrix. Let us denote it as MR, where MR can be defined as Mij n cross n, where Mij equal to 0 if ordered pair AI, Aj does not belong to R, and it will be 1 if AI, Aj belongs to R. So, let us see some examples of it. So, let us say that we are having a set A equal to 1, 2, 3 and there is a relation R defined on this set A. So, how we can represent that in a matrix form? We can represent this as an MR, where if we are having 1, 1, so the first entry is 1. We are having here ordered pair 1, 2. So, the second entry here is 1. Then we are having 2, 1 ordered pair. So, we are not having here the ordered pair 1, 3. So, the third entry in this row will be 0. Now, we are having ordered pair 2, 1 here. So, this entry will be 1. Now, we are having 2, 3. So, this entry will be 1. In the similar way, we can define these two entries here as 1. So, this is the representation of this relation in matrix form. Another example, let us say that we are having two sets A and B containing these elements. So, and if we are given the matrix MR, so now how can we write the relation R, or how can we write the ordered pairs in relation R? So, obviously, where we are having the entry as 1, those ordered pair will be present there, and there the entry will be 0. Those ordered pair will not be present here in this relation. So, let us see its solution. So, here obviously you can say that this 1, 2, this entry is 1 here. So, ordered pair here will be 1, 2. Next entry, that is 1 here is 2, 1. So, it will be 2, 1. Next entry 2, 3. So, in this way we can write all the ordered pairs that are represented through this matrix, right? Let us move to the next term, that is representation of relations as a digraph. So, the graph of a relation, it can be defined as a directed graph having nodes that corresponds to the elements of set A, and the edges between two nodes will be there only if an element X is related to element Y, otherwise the edge will not be there. And if we are having an edge of the form x comma x, this can be represented as a self loop. So let us see some examples of it. So if we are having a set A and a relation R1 on this set A, and this relation R1 is defined as a less than relation, that is ordered pairs here are 1 comma 2, 1 comma 3 and 2 comma 3. So the graph of this relation can be represented as in this way. Here you can say the ordered pairs are represented in the form of directed edges. There is an ordered pair 1 comma 2 here. So that's why there is an edge from 1 to 2. Similarly 1 comma 3, so edge from 1 to 3, and 2 comma 3 edge from 2 to 3. Next example, we are having two sets A and B and we are having a relation R2 here. So how can we represent it? We can represent this graph in this manner, right? So let us suppose we are having a set A containing elements 2, 3, 4, 5 and 6, and we are defining a relation R of type less than. Then how we can define its graph? So 2 nodes will be 2, 3, 4, 5 and 6, and the ordered pair here will be 2 comma 3, 2 comma 4, 2 comma 5 and 2 comma 6, because these are all ordered pairs that are satisfying this relationship. Then the next 3 comma 4, 3 comma 5, 3 comma 6. Again we are having 4 comma 5 and 4 comma 6. Then we are having 5 comma 6. So this is the graph of this relation, that is less than relation, on this particular set A. So now let us see the domain and range of the relation. So if R is a relation from set A to B, then domain of a relation R is defined as a set of all first elements or first coordinates in those ordered pairs. Similarly, range can be defined as a set of all second coordinates or second element in that ordered pairs. So let us see one example of it. So if we are having less than relationship on set A 1, 2, 3. So these will be ordered pairs here 1 comma 2, 1 comma 3 and 2 comma 3. Now domain of less than will be 1 and 2. Set have containing element 1 and 2 because these are the first coordinates of these ordered pairs. Similarly, what will be the range of this relation less than? The range of this relation less than should be 2 comma 3 here. Equality of two relations. That means if we are having two relations, when we can say that these two relations are equal. So let R1 be an n-array relation on A1 cross A2 up to AN. Similarly, R2 be an m-array relation on B1 cross B2 up to Bn. So R1 equal to R2 if and only if we are having n equal to m, AI equal to BI, and R1 and R2 should have equal set of ordered pairs. So let us see with an example. So if we are having three sets A, B and C containing these elements, and if we define a relation R1 that is on A cross B, and we define second relation R2 on A cross C, and these are the relations R1 and R2. So can we say R1 equal to R2? Now if you see it, that is R1 equal to A1 comma 1 B1, A comma 1 B comma 2. Similarly R2 equal to A comma 1 B comma 2. So by seeing it, we can say that these may be equal, but the answer here is no. Why? Because R1 is defined on set A and B, and R2 is defined from set A to set C. So the underlying sets on which these two relations are defined are not same. So that's why even having the same ordered pairs, these two relations are not equal. I would like to ask one question. So what is that question? How many number of relations are there on a set A having n elements? Should be the answer. So let us see how can we solve it. We know that a relation R is a subset of Cartesian product of the set. So if a relation R is defined on a set A, that means R is subset of A cross A. And if set A is having n elements, then the number of elements in A cross A should be n cross n, or we can write it as n square. Now, because R is the subset of A cross A, so total number of subsets defined on this A cross A, we can write it as 2 raised to the power modulus of A cross A, that means 2 raised to the power n square, and that is our answer. This was all for this session. I hope now the basics of relations are clear to you. In the next session, we will start with the properties of relations. Thank you.